Good morning, everyone. Again, happy to welcome you all for the weekly colloquium at IPN. And today we have Philose who will be talking on a very interesting philosophy of science question that has been quite a prominent one. It is titled The Reevaluating Locality and Bell's Inequality, Exploring the Possibility of Non-EPR Local Explanations. And also happy to point out that today we are trying to experiment a new format where we have the speaker and also a discussant. Tarun Menon from APU has kindly agreed to be the discussant for this. Of course, for putting all of this together, I'm really thank Shinod because he's the one who contacted Philose, got in touch with Tarun, made this happen. And sadly, he had, as we all know, some other lecture going on in his department. He can't be here. So what we will do is that, Philose, I mean, generally we have like, say, 40 to 50 minutes for the person to speak. I mean, it's fine, absolutely fine to spread over that point and spread that particular overshoot that time period. And after that, we will have Tarun's initial discussion response, and both Philose and Tarun can probably discuss like say for 10-15 minutes. After that, I think we can open up for the larger audience that we have here. So over to you, Philose. So I'm again happy to have you here. Yeah.
Thank you, Tarun. Varun, let me share the PPT. Hope it is visible to.
Yes, can you just go to the first slide? I don't know whether this is the first slide.
Thank you. Yeah. Okay. Let me begin. So this presentation is on the topic of EPR explanation. So the central issue here is an observational phenomena called quantum entanglement. And Einstein, Podolsky, Rosen, this paper is known as EPR paper. They provided an argument, an explanation of this particular phenomena. And today's our discussion is about this. What is the logical structure of their explanation and what are the other logical possibilities, or what is its relation to a competing explanation, and what does a consequence of that explanation means to this debate. So rather than explaining the debate in its scientific terms, my attempt here is to explicate the logical structure of the debate. That means the hypothesis and its competing hypothesis and some of the major deductive consequences of the hypothesis. So quantum entanglement is just about a correlation. Think of any two correlations. Here we have a correlation between two particles, P1 and P2. So it is easy to think in terms of spin measurement value. This correlation exists in the case of all kinds of measurement. In the case of quantum entanglement, whether it is about position or momentum or all such properties, we can say. But in the case of spin measurement, we can say that whenever the particle P1 shows an upspin value, the particle P2 shows a downspin value. So that means there exists both of them shows opposite spin value. Those are the only two possible spin value that can be measured in the case of quantum particles. So, and now the issue is that how this correlation can be explained. Well, both of them shows opposite spin value whenever it is being measured. And what makes things complicated is the kind of an instantaneous nature of this correlation exhibition. Means when P1 is measured at time T1, and it is not that P2 is measured later at some point and shows a correlation. When both of them measured simultaneously, they show a correlation. And they can be placed at a very large distance. So in the relativity terms, when the particles are at a space-like separation, even when the particles are at the space-like separation, it shows a correlation. So that makes this explanation of this correlation a bit more difficult, because often the correlation is something which can be explained in terms of an interaction between the entities. Here, interaction is a bit hard thing to invoke because of this instantaneous relation, and given the distance between the entities. But the Copenhagen sticks with this interaction explanation. So Copenhagen explanation, the major figure is a Bohr. Bohr is the scientist who responded to this EPR explanation. And the Copenhagen interpretation of quantum mechanics already has certain kind of presuppositions about quantum particles, or theoretical assumptions about the quantum particles, and especially its unique nature of measurement in the quantum system. So, as per Copenhagen interpretation, the particles do not have a measurement value prior to the measurement activity. So that is a very specific, in fact, a weird way of understanding measurement. In the classical case of measurement, we simply record the physical state of that system, of that particle. But here, in the quantum measurement activity, it's disturbed the system. Prior to the measurement activity does not have, for example, a particle does not have either upspin value or downspin value. They are we can say that it has both of these properties, or disposition to show either of the values. Prior to the position measurement, we can say that a quantum particle exists at a particular spatial coordinate. It exists both here and there. But the measurement activity forces the system to adopt or assume one of the particular value. And this is the theoretical baggage of the quantum mechanics, or the theoretical resources of the quantum mechanics is to explain the entanglement phenomenon. So the quantum particles are in superposition. That means they have the disposition to show either of the values prior to the measurement. And then upon the measurement, they assume that the Bohr claim that there exists and they interact instantly, the particle P1 interact with other particle P2. Okay. And this interaction is the explanation why there exists a correlation between the entangled parts. So P1 assumes the value, P1 assumes the upspin value, and it's communicate to the P2 and its entangled partner, and P2 assume an opposite spin value. And this communication, this happens instantaneously. And this is the this interaction is the explanation, instantaneous interaction is the explanation Bohr gives to this quantum phenomenon, entanglement. But Einstein-Podolsky-Rosen explanation substantially different. They are here mainly trying to save a principle called locality. And they adhere with the classical notion of a measurement. Particles do have a definite measurement value even prior to the measurement activity. It is not that the measurement activity changed the system and brought the measurement and brought this definite value into the system. So it simply record the pre-existing physical state. And so their explanation is simple. This entanglement refers to the creation of a pair with a correlated measurement value. Why P1 and P2 shows opposite spin values? Simply because they have had this property or a disposition to show this measurement value even prior to the measurement activity itself. In other words, the entanglement itself is a kind of a combination of combining of two or more particles with opposite spin value. So modeling explain this. Modeling has an explanation, provide an example to make it very clear. Say that, think of taking a coin and splitting vertically and throwing the head side into one side, left side, and tail into the right side. Okay. So whenever you measure the left hand part, okay, you can see that it shows head, and then the other one shows tail. Okay. So there is nothing magical about this correlation. It's simply because they have had this opposite signs from the very beginning, and so that is what entanglement means. Entanglement means that two particles with opposite spin values have been combined. So and here, what Einstein was trying to say, one important principle called locality, and this, at least in the contemporary debate, this locality is the central principle, is the principle that comes to the, assumes the central stage in this entire debate. Because if particles do not have a definite physical state prior to the measurement, then a local explanation is a possible. So here we can, in a simple sense, the locality means that any kind of influences from one event to another is a local one, is a spatially mediated one. So the modeling provide this definition. A physical theory is EPR local if and only if, according to the theory, procedures carried out in one region do not immediately disturb the physical state of systems in sufficiently distant region in any significant way. So once we assume that the causal influences are spatio-temporally mediated, any such influences cannot be immediate. Any such influences cannot be instantaneous. Okay. And this, in fact, this principle of locality is something quite important in the scientific debate, or in the as in scientific practice as such, because Einstein believed that if we give up this principle, then there is no way we would be able to maintain the distinction between the physical and the non-physical. We would not be able to say that, look, this is a quasi-enclosed system. We won't be able to say that this has a very particular specific spatio-temporal location. And these are the assumptions which are quite essential to the scientific practice. And these are the assumptions which are serve as the basis of our even of our intuitive distinctions between physical and a non-physical entity. Some entities cannot be invoked in the explanation of a scientific phenomenon. A ghost cannot be invoked, okay? But some other entities are allowed, because simple distinction is that they are physical and some of them are the others are non-physical. And this distinction is something which is based on the spatio-temporality. In other words, it's based on the principle of locality. So here, this pose a challenge. These two. So now we have two kinds of explanation to a correlation. Okay. One we can call as a kind of an interaction thesis. Why a correlation happens? Because the entities interact. The other one says that no, the correlation happens because of independent of the other entity. So there is something inherent to each of these entities. How to settle this debate? And scientists did not have a clue until the arrival of Bell's work. Okay. Bell deduced a consequence from the EPR explanation. That's what we call as a kind of an Bell's inequality. And if the EPR explanation is true, if the EPR explanation is true, then there exists a limit to the degree of correlation of measurement values of entangled particles. So it's sort of easy to see that how at least we can think of a degree of correlation, because as per the EPR explanation, in relation to x-axis, assume that, for example, in relation to x-axis, particle 1 shows upspin value and particle 2 shows downspin value. In relation to y-axis, assumes that particle shows downspin value and particle P2 shows upspin value. So we can, if these are the pre-existing physical states of these particles, and if these are the cases, then when both particle passes through the same axis, suppose both particle passes through the x-axis, then both these entities show 100% of correlation. But what would be the case if P1 passes through y-axis and P2 passes through the x-axis? Or P1 passes through z-axis and P2 passes through the another axis. Okay. So when particles passes through different axes, we can see that if the values are fixed, if the values are pre-existing, then there would be we can't say that in all possible cases there would be a correlation. In some cases, both shows upspin value. In some cases, both shows downspin value. So that means there would be in 100 of cases, there would be a degree of only 66 of them may shows the correlation. So so there would be a degree of correlation. There is a limit to this degree of correlation. It cannot be 100%. In 100 repetition of experiments, 100 instances of experiments, we can say that only few of them would show a correlation if the EPR's assumption about this physical property is true. Okay. And it's Bell deduced that it is between 33 and 66. But the experiments exceeds that limit. Experiment shows that even quantum particles shows degree of correlation up to 75%. So this is the story in that sense. So there are two explanations. The prominent one is this, the one which you are analyzing is the EPR explanation. And EPR explanation has a consequence. And that consequence is falsified. Therefore, the EPR explanation itself is falsified. So now starts the debate. What does this falsity imply? course, if the EPR, while experimental violation of Bell inequality conclusively shows that the EPR explanation is false. There is no doubt about that. At least there are no questions have been raised on that matter. Okay. But the important issue is that what are the principles that have been falsified? In other words, what are the principles that the EPR explanations invoke to explain this quantum entanglement issue? So then, so a set of principles explain entail a Bell inequality, and the Bell inequality is false. Therefore, this set of principles, is false. So, what are this set of principles? So, there are two major camps, we can say. Locality camp and a conjunctive camp, and there has been a lot of debate has been going on this issue, or a lot of debate has been going on between these two camps. Okay. So locality camp says that only one relevant principle is involved, that is locality. There can be no immediate influence between two events which are separated. Other things, all of those who are involved in this debate agree that locality is a major principle. The conjunctive camp argues that along with locality, there are other important principles like determinism, realism. So my attempt here is not to engage in this debate between these two schools. And as a personal opinion, I stand with the locality camp. I believe that the position of the locality camp, locality is the only relevant principle, is something that is adequately defended in the literature. So my attempt here is to scrutinize this position of the locality. Suppose if locality is and what does it choose? So locality only more than if you are explanation shows that the world is not falsified. And this in about this antecedent condition, okay, whether other principles are involved or not. But all of them agree that if locality is the only principle, then the experimental violation of Bell inequality shows that the world is not local. And here, this is where my contention begins. My concern is that Bell's inequality is a consequence of EPR explanation of quantum entanglement. And definitely EPR explanation invokes the locality. But does the falsity of the Bell inequality shows that the world is not local? And any such kind of an assertion assumes that the EPR explanation is the only possible local explanation. So EPR in that explanation is not a kind of a very specific particular explanation. It's a kind of an explanation that covers all possible local explanation. So this is the question that I attempt to pursue here. That means, is there a logical possibility of a non-EPR local explanation? So here again, it's sort of summary, but it help us to analyze it. So the question is about a correlation. Two cats crying meow. Okay. And one is an interaction thesis. The First one heard, the second one trying, and then instantaneously reacted. The second one is the independent thesis. It's not that. Somehow they have a disposition to cry meow at 8 a.m. So it's no way they hear the other one and interact and respond to that. Both of them have a disposition to, or they are programmed in such a way that they will cry at a particular time. So EPR explanation is something which comes close to this independent thesis. And Bohrian thesis, Copenhagen interpretation, is definitely the interaction thesis. And it's a non-local thesis because the interaction happens instantaneously. So here the question is that the EPR says the disposition to show the measurement value is something just inherent to the system. The cat has the disposition to cry at a particular time. And the independent thesis is simply says that the behavior or the measurement value is independent of the other entangled particle. Now the question which I am raising is that is independent thesis is equivalent to inherent thesis. So the cat cries independent of the other cat. Does it mean that cat cry because of its inherent disposition to act in that? Is there any other possibility other than that? So I argue that the independent thesis is equivalent to inherent thesis only given a certain ontology. So if the ontology consists only of these entangled particles, if no other entities are invoked in the explanation of this correlation other than the correlated entity itself, then the independent thesis is equivalent to the quantum particles are the only entities that can be invoked in the explanation. Then P1 has a value independent of P2, means that P1 has an inherent disposition. Because but if we invoke another entity, an entity other than the correlated particle itself. So I call it as an extrinsic entities other than the correlated particle itself, an entity other than P1 and P2. In the explanation of this correlation, then there is a possibility of an independent explanation, which is not an inherent explanation. So in simple sense, it's something like this. The cat saw an extrinsic entity, which is spatially proximate to the cat 1, and cat 2 saw another extrinsic entity. It could be a dog or another animal. Okay. So both of them cried because of another extrinsic entity, which is spatially proximate to that. So in that sense, the disposition is not something inherent to them, inherent to either of the cat, and they are not interacting each other, but they are interacting to an extrinsic entity. So, and that extrinsic entity is something which is spatially proximate to it. So this is the possibility which I am trying to pursue here. That means we can, what does this a possibility of an independent explanation which is not inherent. Okay. So particle P1 acquires measurement value in interaction with an extrinsic entity E1. P2 acquires in interaction with P2. E2, extrinsic entity E2. And the property that give rise to the measurement values are not inherent to the particles. So this explanation can remain local while violating the Bell inequality, because according to the EPR explanation, the particles have a fixed definite measurement value in relation to a specific measurement configuration. So in relation to x-axis, P1 always show upspin value. Because that is the disposition of that particle. That is the property of that particle. Even if it is yes, if in a repeated experiments, also it shows the exact same measurement. Okay, and this is what I call as a constant measurement value thesis. Okay, the particle shows the same measurement value in relation to a specific configuration every time it is measured. And it's not merely about the quantum entanglement, it's about a quantum particle in general. Okay, so the Einstein EPR Einstein thesis is that they have a specific measurement value every time it is measured. It does not matter. So now the experiment shows that it's a particle exhibit an upspin value, and then if it undergoes another experiment, experiment where it passes through a y-axis, that scrambles the information it processed. In other words, when it passes through the second time, there is no guarantee that it will show the upspin value again. So that itself basically undercut the Einstein thesis of this constant measurement value thesis. But the constant measurement value thesis is the implication of Einstein explanation. And Copenhagen is not bounded by this constant measurement value thesis, because prior to the measurement, the particles are in superposition. They have the disposition to assume any of the physical states. And this extrinsic ontological explanation, I argue that, is also not bounded by the constant measurement value thesis. Since the measurement value is not inherent to the particle can acquire a different measurement value depending on the extrinsic entities it interacts with. So it is an extrinsic entity that determines the measurement value of the quantum particle. So, so here I attempt to explain this extrinsic ontological explanation by providing a very concrete example. This is a complete speculative entity, because my attempt here is to depict a logical possibility other than the EPR local explanation, or a logical possibility other than both Bohrian and the EPR explanation. So I speculate an entity called space path. So across the space-time fabric, there exist small channels or paths that act as conduits for quantum particles. Quantum particles are always situated within the space path, and these channels in the space-time fabric can guide or determines the movements and trajectories of the quantum particles. Okay. So, yeah, so quantum particles are in that sense follow certain kind of a trajectories that already exist in this space-time fabric, and so that means they are always situated in this in space path. Each quantum particles are situated in space path, and this space path is what we call as a kind of an extrinsic entity. So they have some kind of a property. In interaction with this particle, this entity, space path, the particles acquire a physical property. The disposition to display the measurement value is not inherent to the quantum particle. However, they have a disposition to exhibit the definite measurement value even prior to the measurement, as they are in constant local interaction with the space path. So here the extrinsic ontology sort of aligned with the EPR explanation and or aligned with the classical idea of measurement. The universe or the entities have had an objective status. even prior to the measurement activity, and we are simply recording it. Okay. But at the same time, it somewhat comes very close to the superposition idea, because these particles can assume any value they want, and it's though it's being in a though it's being in a definite measurement value, it can change its measurement value at any time. Depends on all what we need to do is to to create an interaction where this particle interact with a new space. So in interaction with S1, a space path S1, particle always shows, for example, upspin value. Okay. But that does not mean that in another set of experiments, particle would show an upspin value, because it could be the case that the particle would be interacting with another space path S2. Okay. So in a certain sense, it assumes this, or it takes the advantage of both of these explanations. It can adopt any value they want, depends on the entities it interact with. At the same time, they assume a definite position even prior to the measurements. And it is the measurement, and so we can't explain this one without accounting for the measurement activity. It is the measurement activity that shifts the particle from one space path to another. A kind of a possibility that I outline is as follows. Imagine a sandy surface with narrow concave channels that act as pathway for water to flow along when the water is poured onto the surface. Now, suppose one of the space path is closed off, causing the water that would normally flow through this path to redirect and create new channels. Space paths can be likened to the channels on the sandy surface, serving as conduits for quantum particles. If a measurement setup obstructs or alters a space path, much like obstructing sandy surface channels, the quantum particles are steered in different directions, creating a new space path. So here the attempt is just to say that how does a measurement activity change the behavior or the measurement value of a quantum system? Because the quantum systems are in constant interaction with space paths. And it is because of that interaction, they have certain kind of properties like spin value. And what does this measurement do? They change the space path, which is in interaction with the quantum particles. And so various ways that change can be envisaged. And most probably the change happens in various ways also. Not only that we can think of it in various possible ways. It's not a single kind of change that happens. The bottom line is that measurement activity somehow obstruct the space path or somehow tilt the space path, but measurement activity forces the particle forces the space paths to transfer the particle from S1 to S2. And this has, in that sense, if still being in a complete speculation, which does not have any kind of a physical evidences, this entity has some kind of a lot of explanatory power, because the particles act both like wave and classical particle. Quantum systems act as both wave and particle. And here in this explanation, the quantum systems are in that sense are just particles. They are just classical particles with different spatial positions and definite velocity, etc. But why still they have a wave nature? Because they follow the trajectories that exist in the space-time framework. But still, that trajectories, they are not fixed path. This space-time measurement activity can change the shape of this space path network. Okay. They can block the space path. They can obstruct the flow, and that kind of an obstruction changes the space path network to evolve. And this evolution is something that happens as per the Schrodinger equation. Okay. So yeah, that's in the sense I was just trying to point out that adopting this explanation, in fact, is consistent with the various other behaviors, various other experiments results, or that are relevant to this, that are related to this double slit experiment or single slit experiments. In one case, it shows like a particle which has a definite position. In another case, it shows like a wave. And why this happens? Why this happens? Because these are different experiment setups, and they change the space path network. They change the shape of the space path network. And here, at least, the concern that we have is that the measurement apparatus is changed from x-axis to y-axis. And yeah, so Varun, that one more time I can take.
Yeah, Philose, I mean, like, how much more time you're thinking of? It's already.
Yeah, I will conclude within 5 to 10 minutes.
Yeah, please, absolutely, yeah.
Yeah, so this evolution of the space path network is, in that sense, is in accordance with the Schrodinger equation. So and there is so here that means we can think of various possible ways, but only the key aspect here is that somehow the measurement activity changes the space path network and force the particle to go from one space path to another. So after the measurement activity, now it is an interaction with a different extrinsic entity. And that's why when one particle passes through the x-axis, and in second, when some intermediate things happen, and when it passes through this, again through the second x-axis, it shows a different spin value, because now it is no more in interaction with the same space path. Initially, it was, suppose it was an interaction with the S1. Okay. Now it is an interaction with an S3. Both of them are x space path in the sense of space path which are aligned with the x-axis of the measurement apparatus. Okay. But they have different kind of a properties, or they have a different kind of a disposition to give rise to different spin values. So, and that is the key thesis which I am presenting here to explain the entanglement, quantum entanglement phenomenon. But there are a lot of things to explain, especially how in the case of there are different experimental setups which closes these locality loopholes, they call. That means there often people attempts to show that locality is still possible because of some loopholes of that experiments. And numerous experiments have been proposed to close those loopholes. Okay. And so, at least in the kind of aspects experiments, the situation is that both particles are shot from the same source, and both of each of them are moving towards A1 and apparatus 1 and apparatus 2. Okay? But the measurement axis of the apparatus A1 is changed at the last moment. Change at the very last moment. So there is no possible, suppose even if my explanation is true, that means that is in space path S1 and the other one is in the space path S2. Both of them are X space path. Okay. And now the measurement apparatus A1 changes from X to Y axis. So as per my explanation, and this means that the particle is transferred from X path to Y path, X space paths to Y space paths. Okay. Now the question would be that how the other space path, the S2, will come to know about this change. And I sort of argue that that also can be explained because the S1 act in a way based on its information, and it does not matter whether the information is right or wrong. So even if they would be able to show the correlation, even if the information that they possess is an outdated one. Okay. In order to show the correlation, they don't need to have an exact accurate information about the other space path or the other particle, but all of them have to act in a very unified way. Okay. That if both the space path act in a unified way, then the correlation can be maintained. Though the reasons for being the reasons for this action could be a false information. So yeah, this in that sense, I kind of my attempt here is to portray a logical possibility, and this often when we talk about EPR argument or the EPR paper, the EPR argument is the one which in a certain sense takes the central stage. The EPR explanation is hardly a relevant part to the EPR paper. That EPR explanation is simply that property is disposition is inherent to the particle. That is hardly a relevant point of the paper. But it is relevant because I argue that the Bell inequality is derived on the basis of the EPR explanation. The Bell inequality is derived on the assumption that the EPR or the local explanations are inherent explanations, or local explanations are the explanation that ascribe the disposition to the particles itself. Okay. Therefore, the particles would be having a definite measurement value in repeated experiments. Yeah, I think I will stop here. Thank you.
Thank you, Philose, for this ambitious attempt to bring everything into coordination and resolve some of the problems. I invite Tarun for his responses.
Okay, thanks. Would it be possible for me to put up a slide?
Yes. You just have to click on the share.
Okay, I can do that. Okay, I'll do that in a second then. First of all, thanks, Philose. I think it's really great that the way you're thinking about this, and I think there's potentially a lot to be gained from going back to the assumptions and asking are the assumptions really as free of loopholes as possible, which is essentially what you're doing, and you've identified this idea that they're talking about the assumptions really refer only to intrinsic locality, when really you could have this other kind of sense of locality as well, the extrinsic locality. I do think that there are problems with your proposed solution or your proposed alternative, which maybe indicate that this distinction between the intrinsic or extrinsic way of thinking about locality isn't really a distinction. That really they're the two things. They're the same kind of thing. But I guess one kind of slight lack of clarity I had about your view, which maybe you can clarify later on, is how exactly to think of these space paths you're talking about, right? So when you talked about them just now, you were talking about X space paths or Y space paths. And now, presumably, when you say X space path, what you mean is a path on which this particle will show a particular X spin value. So there'd be a separate space path for X spin up and a separate space path for X spin down. Or is the spin up and down intrinsic to this? So both the spin and the direction of spin are properties of the space part, not the particle, right? That is how you're thinking. Okay. Yeah. So that clarified things a little bit for me. And so is it also the case that so when you say that a particle could either be on an X spin path or a Y spin path, or it can move from an X spin path to a Y spin path, is the idea that when it's on an X spin path, it only has X spin properties because the properties are a feature of the path, not of the particle. So it doesn't make sense when it's on that path to talk of it as having a Y spin. That only happens when the particle goes onto the Y spin path. Is that kind of your view as well? Just to. All right. So I think the question, the kind of system that you've described this way works works to reproduce these correlations for a very specific case potentially, although I question this as well, which is the particular entangled state you were talking about, which is in quantum mechanics what they call the singlet state, where you have anti-correlations for every pair of measurements, right? That whether you measure X on both sides or Y on both sides or Z on both sides, you'll always have an anti-correlation. One will be spin up, the other will be spin down, right? And sort of you can account for the aspect as thing of like changing the measurements at the last moment by saying that they just dump them into the paths that happen to be anti-correlated, even though they're mistaken in some sense. They're still dumping them onto paths which happen to be anti-correlated still because they're mistaken. And so that leads them to act in the opposite direction from what they would normally do, but acting in the opposite direction still leads you to an anti-correlation. That's kind of your account of what's happening in the aspect experiment, right? Yeah, so but that only works as an explanation if you have complete anti-correlation along all measurement axes, which is only true for a very specific kind of entangled state, which would be the singlet state. There are other entangled states, what are called the triplet states, for example, where you have anti-correlation on some axes, correlation on other axes, lack of any correlation at all on other axes, right? And there, I think it might turn out to be slightly more challenging to reproduce the kind of explanation you gave for the aspect case. And I think there's an even more fundamental problem that you'll have with these kinds of non-singlet states, right? So the singlet state is something like up, down, minus down, up. If you ignore the coefficients, that's how you represent it in any particular basis, in the Z basis or the X basis or the Y basis. But you can have states like up, up, minus down, down, which again are entangled states which produce correlations with some measurement setups. They produce anti-correlations with other measurement setups. They produce no correlation at all with other measurement setups. But I think, like I said, the deeper, more fundamental problem with this is that, look, if you're thinking of the space paths as only encoding the spin state along a particular axis for a particular particle, then if one particle is on the, say, Z spin up state, particle one is on the Z spin up space path, particle two is on the Z spin down space path, those facts about those particles are consistent with a number of different entangled states, right? They're consistent with up, down, plus down, up. They're consistent with up, down, minus down, up. There's a number of different entangled states on which you could get both being on space paths where on the same space path, X space path, one is spin up, while the other is spin down. But yet the measurement statistics are going to be different because the entangled states are different, right? So the space path cannot only carry information about the state the particle is currently. Now, I think you said something about how the space path knows what the other arm, what the state of the other arm, what space path the other arm is on. But even that is not going to be enough, because the combination of the space paths that both are on, the combination of the spin states of both of them is not enough to fix which entangled state you're in. It is multiple different entangled states with different statistical properties, for which, at least if I understood what the space path is, it's just an encoding of what is the spin in a particular direction for this particle. You would have the exact same space path, but you have multiple possible entangled states, right? So the space path would have to encode more information than just what space path this is. It would have to encode more information than just what space path the other particle is on. It would have to encode some kind of information about what is the combined entangled state of both particles, because this is still a one-to-many relationship. Specifying the space paths of both doesn't fix the entangled state. And that would then get much closer to effectively non-locality. I think if the space path is carrying information about some entangled state, and that is what is producing its behavior, then seems like your something along the lines of non-locality would be recovered. So that is just one thought I had about how I don't think the way you currently describe the metaphysics here is rich enough to capture all possible entangled states and their the correlations that might arise. Let me just quickly, briefly, before I finish, I'll make one more point, and then maybe other things we can talk about in the question answer period. Give me a second. Let me just share my screen, because I think this would be more useful if I have it. So this is a version of the Bell inequality called the CSHS inequality. So here I'm just using X1, X2, Z1, and Z2, which is, okay, so you have two particles. X1 is whatever the measurement result would be if it was measured for the first particle. X2 is the measurement result on the x-axis for the second particle, and Z1 and Z2 are the measurement results in the Z direction. Sorry, I have a typo in the Z2 thing. It's the measurement results in the Z direction for the first and second particles, right? Now the measurement results are always going to be either +1 or -1, right? We can say +1 is up, -1 is down. Now here is how the CSHS inequality points out a problem with the EPR explanation. So if you look at that kind of formula I have there, x1 plus x2 times z1 plus x1 minus x2 times z2. For the EPR explanation, this quantity will always have to be less than or equal to 2. Why? Because x1 and x2 can only be 1 or -1. Right? Those are the only, you can only have spin up or spin down when you measure something. So either x1 is equal to x2 or x1 is equal to -x2. Right? So if you plug those two things in, either x1 is equal to x2 or x1 is equal to -x2, it's fairly easy algebraically to show that that equation can never be greater than 2. It can never be less than -2. Right? And so that's a very basic constraint if you think of just the particle having these properties. Now, in the violation of this inequality is that in quantum mechanics, the average value of this quantity, you can't calculate this quantity in one shot because you can't simultaneously measure x1 and z1, but you can calculate the average value of this over multiple experiments. And the average value of this quantity, if you conduct the experiment over and over again and calculate it, it can be greater than 2. Right? This is a violation of the CSHS inequality. The EPR explanation seems to require that any particular instance, any particular experiment, this quantity cannot be greater than 2. And so the average, therefore, cannot be greater than 2 if each particular instance is less than 2. Yet in quantum mechanics, you get average values greater than 2. Now, I think the framework you're offering, the solution you're offering, will have the same constraint as the EPR explanation. I can't see how in any particular experiment this quantity would be greater than 2, because the constraints I'm just talking about are true, right? Like either x1 is equal to x2, meaning either the measurement result of the first particle in the x direction is equal to the measurement result of the second particle in the x direction, or x1 is equal to negative x2. And if those are your constraints, then this is always less than or equal to 2. Now, maybe on your view, you can get around this. So this is why I clarified things earlier. So my initial impulse when I was reading your paper was that your view will have the same issue with this inequality as the EPR explanation does, because there's nothing in your view that says that this can be greater than 2, this equation. But I guess now thinking about it, your view says that you can't simultaneously have an x1 and a z1 value, or an x2 and a z2 value. Is that right? That if something has an x spin value, it just doesn't have even counterfactually a z spin value. Right? It's not. There's no answer to the question: what would the measurement have been if we had measured the z spin instead of the x spin? If that is the case on your explanation, then maybe you can get around this by saying that you can't simultaneously talk about x1 or z1. But yeah, I need more details about that. But this is just maybe a very simple version of Bell's inequality to think about if you're trying to develop this account and to show why your account won't fall afoul of this version of Bell's inequality. So just to wrap up, I think that your account is not going to be able to explain the correlations for all kinds of entangled states without adding a lot of information to these space paths themselves, which effectively make them capable of having information that is non-local. And the second is, it's not clear to me that certain formulations of Bell type inequalities can be accounted for by your explanation. So these are just things to think about. But I'll leave it at that.
Philose, you want to quickly respond, or should we go ahead to the other set of questions the participants might have? Both are fine. I'm just asking. Yeah.
Yeah, I think I will respond to that.
Yes, please go ahead. Yeah.
Varun, really thanks for this valuable input. I don't have any kind of exact response to that, but I'm also just exploring some possible ways to address those concerns. One is that the first one, when we talk about it's not, the correlation is not always anti-correlations or opposite spin value. There are different kinds of correlations exist in that sense. Okay, so so at least one way I would like to address it by saying that of course it's another information or another property that is added to the space path. It's not that space path always transfer the particle to another another space path. Okay. If the correlation is a probabilistic one, okay, that means then the same property can be ascribed to the space path also. That means it's not that whenever the x-axis is shifted from x to y, the space path necessarily shift the particle from x to y, x space paths to y space paths. Okay, sometimes it's simply in the simple sense that sometimes it makes mistakes. Okay, or sometimes that transference may not be accurate. Okay, or so why can't we ascribe the same probabilistic tendency to the space path itself? Okay, or the network of the space path. So in that instance may address the concern that, look, in some cases there is no correlation at all. Okay, and that means this space path is also having this behavior of the transferring behavior of the space path is also in that sense a probabilistic one. The second way I would like to address that point by saying that, look, the definition of correlation is different to the different space path networks. Okay, so it's in the correlation. If it is correlation means opposite value for some space path network, and correlation is same value for some space path network. That means distinct different kinds of networks are. And one network is different from the other network mainly because of the definition of the correlation that they have. Okay, and the definition of the correlation could be in that sense could be changes from one network to another. In fact, I'm not so sure. I'm also not so sure how that would be able to address the concerns related to, for example, this three particle, when three particles are involved in the inequality.
Is it only me that like for which
Yeah, no,
But sorry.
no, Philose, I mean,
yeah,
for a
Philose, we
brief
missed a lot
minute.
of what you said.
Yeah, because of some internet problem, it was not clear.
Am I audible now?
Now it is fine. It's just like for a few seconds it was not clear, but go ahead, please go ahead. Yeah.
The second aspect which I was.
Yeah, Philose, can you quickly recap? Probably you can, as Abhishek is saying, try to turn off your video. That might, go ahead, Philose. Can you quickly recap what you said in the last minute? Yeah.
So the second aspect which I was trying to say is that the definition of correlation could be different for different space path network. So there exists distinct kind of space path networks. Entanglement means two or more particles are placed in a space path network, and there exists a distinct kind of space path network. Means the definition of correlation is distinct for these three different networks. So my response are along the two lines. One is that the space path transferring behavior is also probabilistic, like the correlations are probabilistic, and it's not that there exists a necessary transferring process. And the second is that the correlation, just like we can see different kinds of correlations. Okay, it simply means that there exist distinct kinds of space path network which embodies different kind of embodies different definitions of correlations. Okay? But I think CHS inequality, the challenge I consider as sort of formidable. At least at this point, I do not have any. But you have suggested a way out, and I did not quite understand that. But if that's true, that means if the value would be always less than 2 in the EPR network, and if that is true, then that is a bonding that is same is true for this explanation also. And I'm not, but just want to point out that when you mentioned that how counterfactually, whether a particle has an when a particle shows an x subspin value or an x spin value, whether the question is that whether it has a counterfactually can be sensibly says that it has an z upspin value. One way the answer is no, in the sense that it is situated in a x space path value. Okay, but in some other sense the answer is yes, because later it can be transferred to an z upspin value, z space path. So, but given time t1, whether it can have it cannot even have a counterfactual z upspin value while being in an x space path. Okay, so those are the, I think those are the kind of quick responses that means that I have. I'm not especially in the case of CHSs, I'm not sure whether I have addressed the concern, but at least I'm just trying to think of possible way to go forward.
Thank you, Philose. And I'm presuming Tarun also has something to say, but can I request, if Tarun doesn't mind, others to raise their concerns, questions, clarifications, if Jyoti, Siddharth have any you can raise your hands. Siddharth, you want to go ahead? Since I saw you on mute.
Can I go ahead?
Yes, please go ahead.
Yeah.
I would request others to raise hands, Abhishek or Jyoti, if they have any questions. Okay. Go ahead, Siddharth.
Hi, Philose. Thanks for a very interesting talk. I'm not sure I completely followed various things, especially parts of Tarun's responses. I think because I'm due to my lack of familiarity with the topic and issues itself. However, most broadly, it seems to me that the issue or the question or the problem is the non-locality of particles such as electrons. And your solution to be, I mean, if I may characterize it generally, seems to be that you're saying it's not the electrons or particles which are non-local. However, what appears as non-locality is actually due to what broadly we might call the topography of space-time itself, and the topography of space-time has something called space paths, right? So that way you want to explain what seems to be action at a distance, instantaneous action at a distance or something like that, while not making particles non-local, right? I mean, I'm not familiar with the discourse, but would in some sense a non-local topography of space-time be more acceptable to parties in the debate than particles themselves being non-local? Or would it, I mean, otherwise it might seem like you're just moving the undesirable characteristic from one entity to somewhere else, number one. And second, again, I'm not familiar with the debate, but I think there is a, debate on whether, hey, are space-time, the plenum and the entity themselves distinct, or are they one? I don't know what your, if you're making a specific assumption or taking a position in this regarding this, maybe your solution does seem to assume that they are distinct, right? Yeah, thanks.
Yeah. Varun, may I respond?
Yes, please go ahead. Please go ahead.
Yeah. Siddharth, thanks for that input. I would say that if non-locality is in that sense is locality or non-locality is in that sense a kind of a feature that can be ascribed to universe in general or to the space-time fabric itself, in the sense that if the world is essentially spatio-temporal as it is described by the classical theories, then the universe as such is a local one. Okay. So so both of them are in that sense equivalent. So particles having a non-local causal powers, they can interact in a they can interact each other non-locally, means that that means the fabric of the universe is basically non-local. Okay. But my attempt is not that. My attempt is not to ascribe the non-locality from transfer the non-locality from particle to space-time fabric. Right? My attempt is to defend the local nature of the universe itself. In other words, so far it has not been conclusively proved that the world is not local. And why? And in order to explain that, I introduced this entity called extrinsic entity called space path. The first part is that entity need not be space path, several such entities can play the role that space path has played. In a broader sense, my attempt is this. The EPR explanation is a local explanation which has been falsified. So if you want to save the locality or the idea of local universe, then we need to provide an explanation of quantum entanglement. That means an instant correlation based on some kind of based on some definition of a locality. And my attempt is to state that is quantum entanglement can be explained if we invoke an extrinsic entity into the explanation of this in the explanation. So my attempt was to provide a kind of a local explanation, a thorough local explanation to the quantum entanglement. There I am there I am invoking an entity called the space-time fabric or the space path, and that also has that there also the space paths also interacts locally. The interaction between the space paths are also not non-local. Okay. Yeah, I think that's my attempt is.
Yes, thank you, Philose. Abhishek, you want to go next? Also, I would request Philose, can you switch off the video? Probably, I think that is adding to the. Hey, hi, Abhishek. Nice to see you.
Yeah, hi.
Yeah.
I hope I'm audible.
Yes.
Let me preface by saying that I have but the most rudimentary understanding of Bell's inequality and like what it tries to do. But it seems to me, Philose, thanks a lot for the talk, that you are positing some entity, some external entity or a cluster of such entities, space path, in the fabric of or in space-time. I just want to know if you have thought about whether this is kind of an entity, how it relates with existing physical theories, or have you given it a thought? Because it seems that you are positing some addition to the ontology of that physicists work with. So have you also given it a thought how it relates with the existing, what could be the nature of such space path? Or is it simply a metaphysical device that you are using at this moment to, I don't know, preserve locality in light of Bell's inequalities? I hope that makes sense.
Yeah, thanks, Abhishek. It's right now it's just a speculative entity, and I haven't thought of how consistent it would be with the existing theories or even the theories about the space-time itself. Okay. In fact, I heard that there have been some attempts to explain quantum phenomena by using this idea of space-time itself, but it's not along this line. So definitely there are some parallel discussions in science that connects space-time with the quantum phenomena, and but my debates are completely, that means I haven't inquired along that line so far.
Jyoti, I mean, I'm sorry to put you on spotlight. I'm just asking if you have any questions, you can go ahead.
Hi, Varun. Actually, yeah, sure. The thing is that philosophy of science is not really my research area. I have just studied it during MA level, but I did have a question, and like it's towards most a very basic trivial question, I would say, towards epistemic side. So I think you will certainly clarify it. So when you spoke about Copenhagen's interpretation about the particles do not have a definite measurement value prior it is measured. So I was just wondering, that is about knowledge being discovered or being constructed. So I was thinking along those lines. that only when it is measured, then like the particles, then some kind of measurement value comes up. So is it like knowledge discovered, which exists independent of human thought, maybe, along the lines of realism, or is it something like constructed? So I was not very, so I think I kind of got stuck there. And since I could not follow all the discussion because it's not my area, but maybe you can say something about this.
Thanks, Jyoti. Thanks for that parallel, drawing that parallel, and I am also not quite familiar with that epistemic distinctions that you have pointed out, but I think is to an extent that distinction can be drawn, because if this construction, if the viewpoint of construction asserts that, look, it's not that there exists an objective entity that to be discovered. Okay, it's not that when we know P, it's not that we discovered an entity called knowledge which exists even prior to that knowing activity. But it, in the activity of this knowing constructs something. But so in I would say that in that minimal sense, that
Philose, just to highlight, your voice is breaking.
Yeah, Philose, we can't hear you. I can't hear you at least at all. Yeah.
I can't hear either.
Jyoti, can I request to switch off the video if possible?
Sure.
Yeah, probably that will reduce.
It's still
Philo seems to have left the meeting.
Yeah.
Maybe he's trying to reconnect or have a connection or something.
Yeah, let's see what happens.
He's back.
Yeah.
Varun, am I audible now?
Yes. Please go ahead. But yeah, your response to Jyoti was got scrambled. Yeah.
Okay. So this is the way, that means I will still want to emphasize a kind of a distinction between, that means distinction between this epistemic and this quantum site. That here it's not exactly a kind of a construction like we can think of in the knowledge, in the epistemic side. Okay, because it's just making some kind of a changes in the system. Okay. So the entity, it is still that means this possibilities, even in the Copenhagen interpretation also, the possibilities are sort of predetermined. It's not that it can take any value it wants. It can take either only upspin value or downspin value. Okay. So, and among these possibilities, it is forced to adopt one particular possible value because of this intervention. Okay. So, and that kind of possibility is not something. So, yeah, that kind of determination of possibility is still something which is the part of this quantum site. Okay, but I can't see any such kind of predetermination of the possibility in the case of a knowledge. Okay. So I would rather consider it where one, it is a kind of completely new construction, the epistemic side. I would rather say that the quantum side is not in that sense a kind of a complete new construction, but rather a kind of a intervention in the existing possible system, in the system of possibilities. Okay, so parallel is there, but still I don't think it can be extended like we have like the constructive theories of knowledge.
Right, sure. Thank you, Philose, so much.
Yeah. So Tarun, before we start the second round, if you don't mind, can I just ask you point out few points to Philose?
Yeah. Please.
So yeah, probably then after that we can have the second round of Q&A. Philose, yeah, thanks for this talk. And as I said, it was ambitious attempt. Ambitious for various reasons, because you are quite familiar with the history of quantum mechanics and the various attempts, including Einstein's and various other people's, to bring back the classical imagination, classical understanding of the non-classical nature, to bring back whatever that could be that quantum mechanics tried to disrupt in its development. So in that sense, I think it is very ambitious. I also it appeared to me very much like the mechanical philosophy of the 17th, 18th century, where there is clear path for each and everything connected. Each particle knows which space path it is going to interact with other particle and all of those things. Having said that, I find that, like, say, the solution that you have come up with is very specific, and if I have to put it in a, it's very specific and ad hoc to solve one problem of the larger framework of quantum mechanics. That is to solve locality problem where two particles are involved specifically. I think this attempt will face several challenges. Even the attempt in itself, like, say, even if we confine our problem to, like, say, two particles being entangled and there being special conduits in space through which they are interacting with each other, and the way you articulated it, that, like, say, for a particular property that we are measuring about the particular property, it will have a special path, or the property it will have depends on the path it is going, it is currently lies, will become problematic because once we see, the thing is, one of the problems that the quantum mechanics doesn't actually solve or say much, but it is there inherently in the formulation of it, that you can set up experiments only. Like, when you're measuring a momentum property, you can set up an experiment only for that. And it is only in that setup you can just invoke questions about the momentum property of that particle. You cannot, once you have set up the experiment, you can't invoke spin property, because the setup is not supposed to answer that. So this has led to very fundamental questions about, like, say, what is the actual nature of quantum mechanics? Do a particle has all the properties like spin, momentum, position, or is it has the property only that we are measuring? Because then, going by the way you are trying to talk about and bring back the complete classical understanding of a particle, using space conduit and all, it results to problematic conceptions like, say, then we have to think that the particle is in different space paths at the same time, each of the space paths having particular properties. Then immediately the non-classical nature of superposition, which we know we cannot understand that in a classical sense, arises. Also, it was not clear for me how to, two particle interacting, yeah, okay, fine. Whatever you have given formulation makes sense. But for a single particle in superposition, again, it just invokes very different, much more ad hoc manner way of correcting all of this that you have tried to put. But having said that, the larger point that I want to bring it to your notice is that, like, say, the Bell's inequality, what Tarun also pointed out, the other kinds of equality have been brought in, and to solve them, they're not trying to specifically invoke the classical physicality of the particle. Is the particle is in position 1 or position 2? The statistical analysis the quantum mechanics raises is we have to understand at the ensemble level. Like say, given that, like say, I have 100 particles, how the ensemble behaves with the particular setup that I have made and all of those things. And once we understand statistics, not trying to solve or not trying to say what each particle is doing, but like say in a group of 100 or 1,000 or that many number of particles, how a bunch of particles get distributed. That is where the statistical role and importance and emphasis comes in quantum mechanics. So it's not exactly to describe each particle per se. It is to describe how the ensemble gets distributed. And once we understand that the statistics comes in to articulate, describe the ensemble and not a particular particle, various important insights emerges. Like say, for example, Ben's inequality is not about the specific particle, but about how 100 particles get distributed in a specific manner, and when the inequality works or not, and all of those things. Prior to that, I hope you are also aware of various other problems that were raised for EPR, which one of the famous one is the Cochin-Speckers inequality as well, where it is, forget measurement, even before we think of measuring, can a complete allotment of measurable values can be given for an ensemble. And Cochin-Specker shows that this distribution, this way of allocating for 100 particles complete description is not possible within the Hilbert space. And what I also want to bring it to your notice is that, like, and this is what is, I think, is very exciting, given quantum optics and various other statistical analysis that have come in trying to understand quantum mechanics of light, particles, and all of those things, is that the fermions and bosons have different statistical nature. They don't share the same statistics. Bosonian statistics and fermionian statistics are very different. And the ensemble of an electron behaves very differently from an ensemble of photon. And it is to solve this larger problems, we need to invoke entanglement, superposition at the ensemble level. And I don't know whether going by trying to describe each particle per se, how it is evolving or not, becomes a very tedious task and something the quantum mechanics has left far behind. So yeah, just thought of sharing these points. I would love to hear your thoughts about it.
Thanks, Varun, for those inputs. Again, I don't have any conclusive responses to any of those points, but some kind of line that I would like to explore or defend is still classical. I agree that. But at least I don't think that Bohmians are in that sense a kind of neoclassical or kind of neoclassical as Copenhagen projects. Okay. Bohmians are definitely non-local, okay. But they defend exactly this particular nature and its specific and all other characteristics, specific characteristics that can be ascribed to those particles. Okay. So in that sense, so at least in the, I think in Bell remarks or something, this most of this theoretical unconventional images that the Copenhagen interpretation have projected are not exactly a kind of exactly something arises from experimental compulsions. So they are experimental. We can't say that this when we say that quantum particles have moved ahead from that point. In terms of experiments, I would still say that as long as the Bohmian remain as a kind of a contestable candidate of this interpretation, it still makes, and it's, I would say that it's still the most sensible and conceptual one, as in terms of conceptual clarity, not merely because it's adhered to the classical notions to an extent. Yeah.
Yes, thanks, Philose. Yeah. Tarun, you want to go next?
Yeah, I just have a couple of things that might just be comments and then maybe a clarification about your paper based on the answers you've been giving so far. So one is just a broad comment about the space for this kind of solution within a larger philosophy of quantum mechanics, which is, look, the kind of version of Copenhagen that you are describing, which I think there's questions about whether this really corresponds to Bohr's view or not, but the broad idea that you have this particle in a superposition state or a quantum state, which then collapses when you encounter a measuring apparatus. This particular way of thinking about quantum mechanics has radically fallen out of favor, especially among philosophers of physics. And the reason for that is that there's this basic commitment or metaphysical commitment that a lot of philosophers of physics have, which is that as far as possible, we should think of composite material objects, like large macroscopic objects, in terms of the properties of their fundamental constituents, like the atoms that make them up, right? And a measuring device is fundamentally made up of atoms that are atoms just like there are particles just like the particles being used in EPR. And so the answer is we can't treat the measuring device as fundamentally physically distinct from the particle itself. Right. So the idea that the particle engages in this quantum behavior of superposition and so on, the measuring device inhabits this classical world where it disrupts the quantum behavior of the particle and turns it into a classical state. That is something people are dissatisfied with because that is kind of dividing reality into two different segments. One kind of classical world, one kind of non-classical or quantum world. Now, this has some historical relationship to Bohm's ideas of duality and so on, but I'm sure Varun would be in a much better place than me to talk about those. But at least contemporary philosophers of physics tend to reject that idea of splitting reality into two. And it seems like your way of thinking about or your suggestion for how we should think about quantum mechanics has a similar distinction, right? You have on the one hand quantum particles which follow these space paths and so on, and then you have macroscopic objects or measuring devices which play the role of blocking space paths. Right? They themselves are not quantum objects following space paths; they are blocking space paths or rechanneling space paths into other space paths and so on. But the same kind of response that is made against Copenhagen could be made here, which is that look, your measuring device, your large macroscopic object, is also just made up of a bunch of particles that are following space paths, presumably, right? And so really, this has to be some kind of story about the interaction of space paths, where the simple intuition of imagine just blocking a channel in the sand and the water going around it, that doesn't really work because here you don't have two separate things, the water and the blocking device, right? You really just have a whole bunch of channels of water in the sand interacting. And you need to somehow come up with a theory that accounts for the statistics using those mechanisms. But that is kind of a broader thing about how this connects to the interpretation of quantum mechanics, something to think about maybe. I did want to, so one thing I meant to mention in my comments, but I forgot to mention, is that and this became clearer to me as I heard more about what you were talking, is that I think, look, the Bell's inequality literature and all the responses to EPR, what they seem to have established is that one cannot account for quantum statistics by talking about the dispositions that particles have to behave in certain ways, and then maintaining locality. If you just have locality and you just have the dispositions of particles, then you can't recreate Bell's inequality. Now, your response is to say, well, why just focus on the intrinsic dispositions of particles? Why not include this other entities, space paths? But it sounds like anything you could say about the interaction between particles and space paths can be retranslated into a theory about the intrinsic dispositions of particles, right? If you say that you have this space path that has a disposition to dump, so you have an X space path that has a disposition to dump the particle into a y-up space path if it encounters this particular measuring device. You could express that all in terms of dispositions the particle has. The particle has an x-up property, and it has a disposition to change its property to y-up when it encounters this particular measuring device. It seems to me like you can translate anything you say about the local interaction between particles and space paths into a dispositional story about what is going on intrinsically with particles. Of course, particles can respond to measuring devices, so it's not purely intrinsic. The particles responding to measuring devices and changing their properties accordingly, what Bohmians would call contextual behavior. But I think Bell's theory, the kind of Bell's inequality literature has proven that even with this kind of contextual dispositional properties for individual particles, you still cannot get a local theory that matches quantum statistics. You still need non-locality. And it seems like if you can translate your view, as it seems to me you can, into a contextual theory of the dispositions of particles, then you end up with the same problem. So it seems like your theory could not work the way at least I interpret it. And the final point, which is just a clarification I want on your paper. This is on sort of page 13 of the paper. You talk about this situation where you're trying to address the idea that what if you make a decision at the last moment for both of the measuring devices, right? And you say something like this. You say, well, in this case, so I'm reading it out. In this case, S1 shifts particle P1 to a space path where it would show a y-up spin value because S1 thinks that P2 is an S2, where it would show an x down spin value. Now, I don't understand this. If S1 thinks that P2 is an S2, where it shows an x down spin value, why would it only send particle P1 to a y up spin value? Why not also to a y down spin value? Because in general, if you have two particles which are in a singlet state, and you measure the x spin of one of them, and it shows up as x up, and then you measure the y spin of the other one, it could show up as y up or as y down. 50% of the time it will show up as y up, 50% of the time it will show up as y down. So it's not the case that if one path knows that the other is on x up, it will only send it to y down. It can also send it to y up. Experimentally, we have that evidence. But if that is the case, if the path then has a 50% chance of dumping it into y up and a 50% chance of dumping it into y down, and the path on the other end has the same 50% chance of dumping it into y up and y down, you haven't explained the correlations. Why don't we end up with a situation where sometimes both x paths dump it into y up, or both of them dump it into y down? Why is it always anti-correlated? Why does one dump it into y up and the other dump it into y down, or vice versa? That correlation, I don't see how that is explained by your explanation here. So those were the thoughts. Yeah.
Varun, just again a clarification. That means if about the last part, if it does not send to the y downs path, okay.
Yeah.
So then there is no correlation at all, right? Then the experiment does not show the correlation. So,
yeah. So if you measure x up on one side, okay, and y on, so if you measure x on one side and y on the other side, right? So one direction you're measuring x, the other direction you're measuring y. So initially, let's say both particles started out on the x up. The one particle was on the x up path, the other was on the x down path. Let's assume, right? Because initially both detectors were set on x. Now you change the right side detector to y to measure the y spin, right? So now the particle that's on the x down path, that path has to switch the particle to either the y up or the y down path. And my claim is it's not going to switch it definitely to the y down path. It can switch it to, it will 50% of the time switch it to the y up path, 50% of the time to the y down path. How do we know this? Because we can look at the statistics. If you measure x spin in one direction and y spin on the other direction, you won't end up with any correlation, right? You could get x spin up or down and you could get y spin up or down. There's going to be no correlation across those. And it's only when you measure spins in the same direction on both sides that you get the correlations.
At least to that, a kind of again a very broad response is that if the correlation that we can observe is statistical. Okay, then why can't we ascribe what prevent us from ascribing the same statistical nature to this space path transference also? Okay, can't we? It's not that if the experiment shows that the correlation is not correlation is a statistical, we can the same we can why can't we in order to explain that all we have to do is to ascribe that statistical tendency to the space path network also.
This case is a perfect correlation, right? So in the case of the singlet state, if you measure the y spin on both sides of the apparatus, you will always get anti-correlation. You'll always get one being up, the other being down. You'll never get, it's not imperfect correlation where, okay, that anti-correlated, but not 100% anti-correlated. They are 100% anti-correlated. So you can never get a situation where both are up or both are down if you measure y spin. But I don't see how that can be accounted for on your thing. What rules out the possibility of both of the parts dumping their particles onto y up, or both of the parts dumping their particles onto y down?
Yeah, thanks for that input. I think I have to think about it. And the first one is also again that means I'm banking on the distinction of this measurement apparatus and the particle. Okay, and while the measurement apparatus itself consists of this space path. Okay, so but is there a way of claiming that distinction that when we are concerned about this macroscopic behavior, that means the behavior of that set of atoms, set of atoms as a measurement apparatus. That means when they behave, a kind of behavior that is that comes from a macroscopic entity. Okay, and the other one is that when we are can we somehow address that concern, or by not exactly maintaining this classical and neoclassical world, but it's of course it's close to that, but a kind of a behavior of a macroscopic entity and a behavior of a microscopic entities. That means the same set of entities, but the behavior is at the two different levels. Okay, and it's I'm not saying that it's definite response, but something along that line will help us to address that concern. Yeah, I was just thinking aloud, and this, but against this one, I think I am more. I would assert more against the idea of this disposition of this intrinsic idea. So sorry, the idea that the all set of inequalities that have been formulated along this Bell's original inequalities shows that any such intrinsic ascription, ascribing some kind of intrinsic property to a quantum particle won't work. And your claim is that at the end of the day, when I introduce a new extrinsic entity, that extrinsic entity also is in somehow give the picture of an intrinsic system. Okay, particle plus space path. So instead of merely saying that particle has a disposition to behave in a particular way, you are saying that now this system has a disposition to behave in a particular way. And
that is not exactly what I'm saying. I'm saying that it's that system where you have a particle plus space path is, I guess, isomorphic to a situation where you just talk about the particle and then just expand the list of dispositions the particle has, right? To include what in your system would be the interaction between the particle and the space path. I don't see why you couldn't have a completely structurally isomorphic theory where these are all properties that are dispositions of the particle. Where you talk about the space path diverting the particle to another space path, you can just talk about a disposition of the particle to change its properties to different properties or something. So if you have these two structurally isomorphic things, and one of them is vulnerable to Bell's inequality, the other one should be as well. That's the argument.
Yeah, I think, yeah, I will keep that in mind. Thanks for the response. I don't have anything other than that.
Any other questions, people? Okay, if not, Philose, thank you for taking out time sharing the paper with us. I also thank Tarun for being in Delhi and still taking part with all of this. And Abhishek, hello. And nice to see that you have a paper. So anyways, chalo people, anything else to add? Last remarks? Nothing. Okay, fine. Chalo. Bye-bye. Take care.
Thank you all.